Welcome, physics students. This is Mr. Jones here. I'm going to be taking you through a brief 2D kinematic overview. We're just going to have all the important parts you need to know and commit to memory in order to solve projectile problems. So let's get going here. Projectile problems. What is a projectile? It's an object that travels in two dimensions, acted only upon by the force of gravity. Well, what is that force of gravity on Earth? Let's call it negative 9.81 meters per second squared. What does this negative sign mean? Well, we're in two dimensions, so let me give you guys the two dimensions. We got y and x. Well, what does this mean? Negative, well, is acceleration pulling up or down? Well, it's pulling down, and that's what the negative means. And in the 2D world, down is in the y direction. Down. If I were to throw a football here, it looks something like this. And the only force acting upon this is in the downward direction. It's in the negative y at 9.81 meters per second. So now if I said the only acceleration is in the negative y direction, what does that mean about the acceleration in the x direction? Well, that means there's none. There's zero acceleration. It's not accelerating in the x direction. And you can see this when you go outside, and let's talk a little bit about the path of a projectile. We can see this. I mean, it's very clear in the ping pong picture that's shown in the packet. But, I mean, you can go outside, throw a football. We're neglecting air resistance in this physics class in regards to all problems. So we're going to say it's going to be a perfect parabola. When you go outside, you throw a football, you see a parabola, right? It may be a little bit not perfect because there is air resistance. But for the most part, you get a parabola. So we're going to call negligible air resistance as leading us to the path of our projectiles being a perfect parabola. Alright, good. So let's move on. The next part says, horizontal motion has no effect on the time it takes the object to fall. And we can see that here in this picture here. Here in this section, the ball is just dropping from zero initial velocity. And here, we have a velocity initial in the x direction. What do we notice? The time it takes is lined up exactly at each interval of time. And what's here? This is the ground. They hit the same time? Yes, and we saw that when we dropped the balls in class. You saw this exact thing in class, and you can also say that when we shot that the rubber ball at the monkey in the back of the room, one had an x component of initial velocity, and the monkey was just dropping. It had no initial velocity in the x direction. And what happened? They met up at exactly the same spot. Alright, so this is important to note, because when we draw the VAT tables, we saw this in class, we have x and we have y, d, vi, vf, a, and t. What we'll find is the separation will stop there. We can use this time in this column for both the x and the y. Now, if we turn the page over and we read this next section here, it says, when solving a problem, there is no mixing of variables in the x with the variables in the y. The only one that can be mixed is this time, because there's no separation. But if you see, this line right here separates x and y. So when we are looking for something in the x column, we can only use variables in this x column. Now, this might not seem this clear, so let's do an example. Let's work through an example, and then I'll show this in a way where the x will be red and the y will be, let's say, blue, and it'll definitely be more clear. So let's look at an example. Alright, so here's the example. It says, the stuffed free-fall dog is tossed horizontally off the roof of Binghamton High School. The dog falls 18.2 meters to the ground. If it lands 12 meters from the base of the building, determine A, the time it's in the air, B, the initial velocity, and C, the x and y components of final velocity. Well, we have a word problem. We don't really know exactly what's going on, so let's say the first step, regardless of what the problem is saying, we draw a picture to the best of our ability. You may have to read the problem a few times to really find out what's going on. So draw a picture. This is always the first thing. We're going to draw a diagram. Now here's the diagram that it gave you. We're going to have to label this a little further. It's two dimensions. Let's call this our y, and we'll call this our x. Now we have two dimensions. Now let's draw our divat table, because this is going to be important here. D. Alright, so let's take a closer look at this problem now. So now we need to go through the problem and pick out the x components or the y components and try to follow this divat table the best we can. So let's see. The stuffed free fall dog is tossed horizontally off the roof. Horizontally, that's in the x direction up here. Now, does this vector that I just drew, that's 100% horizontal, does it have any component in the y direction? No, it only has a component in the x direction. So what does that say about our VI in the x direction? Well, it says there is one, but it doesn't really have a number. What does it say about our VI in the y direction? Well, if it's all in the x direction, is there any component in this vector right here that's pointing in the y? No. So the VI downwards in the y component is 0. Now, reading through these problems and figuring out what's what is going to be one of the more challenging tasks. So we definitely need to think about it, read it as many times as we need to try to make sense of what's going on. Let's take a look at the next part. The dog falls 18.2 meters to the ground. Well, it's falling 18.2. That sounds like it's going down in this direction here. So that tells us something about this height here. That says that this is 18.2 meters. Now, let's read on. Let's see what else we got. If it lands 12 meters from the base, well, here's its landing, and here's the base. That means that this displacement must be 12 meters. Now, this is displacement in the x direction, so this is dx is equal to 12. And this is displacement in the y direction here. So this is dy is equal to 18.2. So now we fill out our chart. This is 18.2, and this is 12. Now there's one thing that I left out purposely to make a bigger deal out of it. We know that this displacement is a vector, and that has both distance and it has both direction and a magnitude, right? We have our magnitudes in there, but now we just need to double check and make sure everything works out. Let's look at the x column. We know that this is 12 and this is to the right. This is our x, so we're starting here and we're going to the right. It's landing further to the right than it started. Is that positive or negative? Well, it's going to the right in the x, and we know that to the right of the x is positive, so that makes sense. But now let's look at our y. We start up here, this is where we start, and we're falling down. What do we know about the y? Well, we say that up is positive and down is negative. So if we went down 18.2 meters, that means that's negative 18.2. And that's very important that we call out this mistake, because this will change what happens throughout the problem. We'll change different numbers and it will give you wrong answers. So we need to be careful. So we'll add this negative there, we'll add the negative right there. Okay? So our displacement in the y is not 18.2, but it's negative 18.2. Alright? Well, there's something else we can fill out in this chart. That's pretty much all it says in the problem. But what do we know about projectiles? Well, let's turn to the front page and let's read real quick. It says a projectile is an object that travels in 2 dimensions acted only on by the force of gravity. So is that what we have here? I think it is. And what does that say about our y direction? Our y component of acceleration? It's negative 9.81. What does that say about our x component? Well, let's go back to the first page. It says then there is 0 acceleration in the x direction. This is important because the problem didn't exactly spell this out for us. We found this out because we know about projectiles, and we know that the only acceleration of projectiles is negative 9.81 in the y direction. And we know it's 0 in the x. So that gave us more information that we needed. So now that we have our divad table filled out, there's no more obvious information that I can find out. That's probably one of the more complicated parts of the problem. Because actually you need to think about it and make sure these numbers are in the right spot, because if they're not, it'll lead to a wrong answer. And even more importantly, if you guys don't include direction, this negative sign right here and over here, then that's going to lead to complications in your solutions as well. So let's look at the x. When I'm looking at the x, we talked about this. It says when solving a problem, there's no mixing of variables. So if I'm looking at the x direction, I'm only looking at this column here. Well, what do we have? Do we have a t? We don't. Do we have vi and vf? We don't. We only have d and a. And when I look at these equations down here, I only know two things, and each one of these equations has 4 unknowns at least. So I can't use any of those, because what could I solve for if I have 2 unknowns? So we can't do anything with the x column right now, but let's take a look at the y. We look at the y, and we look down here, and we have d, vi, and a. Now, what do we want to find? Well, let's look at, in the example, a says the time is in the air we want to find. So let's solve for the time here. Now we have 4 unknowns, and we can find an equation that has all 4 of these things. And can you find it? 1, 2, or 3? Which one is it? It's this one, right here. Now we can only use our values in the y in this y column here, and we're solving for t right here. So let's do that. Let's go through the solve. Let's go through the process here, and then let's fill in our divat table and see what we have. So here we have it. We have our equation here, and then I took the numbers right off our divat table and plugged them in this line here. Now, what do we notice about this part right here? 0 times anything is 0, right? So we can just erase this and forget that even ever existed. Right? Now we have this. Now, this is the algebra part of the problem, guys. We're taking 1/2 and we're going to multiply these two numbers together. And what do we get when we do that? We carry down the rest of the problem. Negative 18.5 is equal to, well, what is 1/2 times negative 9.81? Well, you can just throw that right in your calculator, and it turns out it is negative 4.905. We bring down the t squared, because all we did was multiply those two numbers together. Now, how do we get t squared all by itself? Well, we got to divide by 4.905. Divide by negative 4.905. And what do we get when we do this? A negative divided by a negative is a positive, right? And what's 18.5 divided by 4.905? You can throw that right in your calculator and you'll get 3.6 is equal to t squared. Now, how do we get t alone? We want to get rid of the squared. Well, we take the square root of both sides. And you get t is equal to 1.9. And we'll throw seconds in there. Now, what does this mean? It means we can go into our divat table. So here's our divat table. And we just found out that our time is equal to 1.9. Now I'm going to do this in green to show that this works. This time here goes with the x column and the y column. Alright, that's very important. We just found time. Alright, so now that we added this next new part here, we solved A. We know that the time it's in the air is 1.9 seconds. So now let's look at the next part. It says B. Find the initial velocity. Well, we know the initial velocity in y is 0, and it says it's tossed horizontally off the roof. So we know that we need to find the VI of x. So we want to find VI. Well, let's pull up our equations again. Let's take a look. Now we have T, A, D, and we want to find VI. So we have D. Let me do this in red so you can see. We have D, VI, A, and T, all in the x column. We're looking for this VI here, right? So what equation has these four? Well, it's the same equation we used last time. We'll just be solving for VI this time instead of T. It's equation number 2 right here. So now we're going to use only the values in our x column. Okay? which we just found out include 1.9 because they can go for both. So let's use this equation, let's plug in, let's see what we get. Alright, so here we have it. Here we have our equation pulled off right from equation number 2. And here I subbed in all the correct values from the x column only. The only thing that's different here is that we had the time. That's why I put it in green, because it was green on the table. And now all we have to do is algebra. What do we see here? We see this 0 right here. And this is very important because what's a 0 times anything? 0 times a half is 0. 0 times 1.9 squared is 0. 0 times a million and a billion and a billion is 0. So this whole term goes straight to 0. This is 0. So we can forget about that in the same way we forgot about that other term before. So now we're left with something that looks like 12 is equal to VIX times 1.9. Well, what do we do to get VIX all alone? We divide. Oh, I had the eraser out. We divide by our 1.9. We divide both by 1.9. And we get VIX is equal to, well, what's 12 divided by 1.9? Turns out it is 6.3. This is meters per second. So now we just found out that VIX is equal to 6.3. So what do? We throw that right back into our DeVat table. Our DeVat table is becoming more and more complete, and we'll see that's the point of this as we go through. So now we can see our DeVat table is a lot more full. We just added this piece in here, and we found that using equation number 2. So now, if we look back to our problem, it says the x and y components of final velocity. And then our DeVat table is completely full. We've answered every possible question they could have asked. Let's see. Well, we can think about this a little bit, just in terms of thinking. If we have a VI, let's say your car is going 6.3 meters per second to the right, and it's not accelerating. It's not speeding up or slowing down. At a time of 1.9 seconds later, how fast will you be going? Well, your VI was 6.3, and you're not accelerating, you're not speeding up, and you're not slowing down. So your VF is going to be equal to your VI, which is 6.3. In a million years from now, like in deep parts of space, if you throw something and nothing is affecting it, it's not accelerating or it's not slowing down, it's not speeding up, it will continue to go the same speed that it was going. In this case, it's a velocity because we have direction. So our VI in the x column is equal to our VF, so we can throw that in there. And now we can see that our whole x component here is filled up. Now, if we look at the y, that's not the same because we have an acceleration. But we've done this before. We've done this plenty of times in one dimension. And all we need to do is look at these variables and these values that we have for these variables only in the y, and do something just like we did before. We have d, vi, a, and t. We're solving for vf. So we need to pick an equation out of our list of equations, 1, 2, and 3. And for this one, let's just pick a simple one. Let's pick equation number 1. Vf is equal to vi plus at. Now this is the acceleration in the y, this is the initial velocity in the y, and this is vf in the y. Let's see. Well, vf we don't know, so we'll just call that vfy. Is equal to vi, 0, plus acceleration, negative 9.81, times our time, which is 1.9. Notice again, these are all taken from the y column of our DeVat table. Okay? So now all we need to do, this 0 cancels out here, it doesn't, plus 0 is plus 0. So all we need to do here is multiply these numbers together. And what do we get? Well, we get negative 9.81 times 1.9 is negative 18.6 meters per second. And this is our velocity final for our y. Now what we're going to do here is we're going to add this to our divad table, and we'll conclude after that. So there we have it. This is our divad table. Any question, all the questions that we were asked, the time, we have our time right here. We were asked for the initial velocity. We can read that right off this chart, here and here, and then we know our x and y components of final velocity, here and here. So the important thing is to stay organized and follow these steps. You know, the picture came into a lot of help when we needed it, and then we just started being organized in this chart. And now your homework problem is gonna come up in a minute here. It's going to be a similar problem, and all right, here it is. It says a bowling ball, a mass 7.5 kilograms, traveling at 10 meters per second, roll off a horizontal table. All right, 1 meter high. Assume the acceleration due to gravity is 9.8. You know what? Let's change this to 9.81. All right. Just use regular acceleration, 9.81 meters per second squared, and the effects of air resistance may be ignored unless otherwise stated, which it's not. All right. So here's your homework problem. I'm going to get you guys started. Let me just tell you, this is. Let me see here. Let's get some red. Let me just get you started with a brief picture, because the first step is to draw a picture. So let's say we have a table here, and our bowling ball has a VI this way. It says our VI is 10 meters per second of a horizontal table. So the second this turns into a projectile, this ball has something that looks similar to that. All right? So we just saw that. VI is all in the x direction. I'm just giving you a couple hints here. And it says that this is 1 meter here. All right? So see what you guys can do with it. I want to see a divad table. I want to see a picture drawn a little better than this one here. And what I want you to find is I want you to find everything. I want you to put it in the divad table. You have d, vi, vf, you have acceleration, you have t, and you have x and y in each one of those components. So you got to figure out what this problem is telling you, what you have, and what you need to find. I will tell you that this piece of information here, you don't have to worry about. Alright? Because did we use anything in the last problem having to do with mass? No. So we don't have to worry about that here. It's just, it's just telling you the mass of the ball, and it's traveling at 10 meters per second over a horizontal table. All right? See what you can do with this problem. This is homework. It's due Tuesday, tomorrow. So give this a go, and thanks for listening. Mr. Jones out.